terms of temperature. So, okay, let's go to hydraulics. So, in hydraulics, let's say we have a pipe. This is our control volume. This area is, let's say, A. Density is rho, as usual. Length is, let's say, L. Pressure this side is P1. This side is, let's say, P2. The velocity is V. And volume flow rate is V dot. This is volume flow rate. And this small v is velocity. So let us assume perfectly laminar streamline flow. So simplest case, then we can write its element mass is rho into area into length, that is mass into velocity. This velocity v we can write as volume flow rate divided by area. So this is volume flow rate divided by area. So that's the momentum. We take its derivative. We take its derivative with respect to time. If it is constant, then rho A will also cancel out. E dot by dt. This will turn out to be the difference between forces, driving forces. So P1A minus P2A. So we have here rho L by V dot. Okay, so I can write rho L by A times V double dot equal to 1 minus P2 equal to delta P. So here, this is dF by dt. This is my equivalent mass parameter. This side, this delta P is E. So E is equivalent to delta P in hydraulic domain. F is V dot in hydraulic domain. So we have this relation. So what we have, equivalent mass parameter here turns out to be rho L by A. So equivalent is rho L by A. Whereas control volume mass was rho A L. So some people by mistake put inertia rho A L. That is not true. Rho A L can be used as inertia when effort variable is force and flow variable is velocity. Whereas in hydraulic domain, our effort variable is pressure difference and flow variable is volume flow rate. So the inertia parameter is actually rho L divided by A. So this will be represented L by A. Here, driving effort is pressure difference and flow is volume flow rate. This is of course hydraulic system. Okay, so that's another definition of inertia. So we have inertia in mechanical domain, that is mass, we have rotary inertia, we have inductance, we have hydraulic inertia, and so on. We can go on defining, except we cannot define it in magnetism, we cannot define it in thermodynamics. Alright? So I hope that is clear. So we can move to C elements, that is compliance elements. While there are not many inertia elements, there are many compliance elements because you know thermodynamics energy is always stored in terms of potential energy. So lots of ways potential energy can be described, whereas kinetic energy you have only very few systems where it exists. So we will go to C element or capacitive coupling. So there are various complex C elements. I will drop those because in your course those are not relevant. Right. Those may be useful in master's level courses. So the simplest C element is shown like this with parameters. This side is system. And it has a relation E, F, we have effort is some parameter, constant parameter times flow dt. Or you can write it its differential form. So example, simple spring. Okay, spring. Or this is torsion spring. T. So these are simple springs which store potential energy. And we know for this, F is K times integral of x dot dt. This one, torque is kt times integral of that dot dt, and so on. So this can be shown as C is to K. This will be shown as C is to KT. Of course, this side there is system, which I am not writing. So these are very simple springs. The way we store energy, that potential energy we store, so that becomes a spring. Alright. So another way of writing this spring, let's say you have a solid bar, cross-sectional area A, force applied F, length is L, Young's modulus is E. And here you have a torsion bar, torsion P, length again is L, its modulus of rigidity is G, and its polar moment of inertia is IP, that is polar moment of area. Polar moment of area. So what we know, delta L by L for this case is A E by L. For this case, delta theta, sorry, not delta L by L. Uh, F by delta L is AE by L. We know delta L is FL by AE. From that we get this. Similarly, for this torsion, we know delta theta is G times IP divided by L. So we can write P torque divided by delta theta from TL by GJ formula equal to G J instead of J I have written IP by L. So this is a torsion spring, this is a linear spring. So we write this T is to K is equal to E by L. Here, this is the torsional spring, it is GIP by L. So we can extend this same logic to, let's say, bending. In massless cantilever, with, let's say, force F applied here, then it's L, E, and so on. I, all those things are known. So we know delta is FLQ by DEI. So we can write F by delta F by delta as CEI by L cube. So this is basically a bending stiffness or linear stiffness. We write here a bending equal to CEI by L cube. So this here is assumed no mass, massless. If you have many such loads, then you cannot represent it by a single spring. You have to write a field element. So that I am not going. Suppose you have this or whatever, one F1, one somewhere F2, some F3. Then what you do, you might have already read in your UG course, find influence coefficients. But get stiffness matrix. In that case, here you know effort is force and flow is the deflection here, delta dot. In that case, you will have multi-port C. If you have three, you will have three. You will have multi-port. One here effort is F1, here effort is F2, here effort is F3. If this location is A, this location is B, this location is C, then you have F equal to delta dot at point A. This becomes delta dot at point C. This is delta dot at point B, and so on. So this becomes multi-port. It's not there in your course. So I am not going into details of this. Okay? So if you have single beam with single load, you have single port C element, that's there in your course. All these are simple things which are there in your course. For multi-port, we are not going to handle it in your particular course. So in electrical domain, we know capacitor. See, so for this, we already know that delta B is Q by C, is 1 by C integral IDT. So you have here C element, here effort is potential difference, flow is current, and the parameter here, you see here, it's 1 by C. So we will put 1 by C. Okay. So your parameter here, unlike stiffness K, AT, and so on, we will use 1 by C. That is the difference with electrical domain. Let's move to magnetic domain, we will see later. Let's move to hydraulic domain. Yes, Hitesh. Ask. Hitesh. Hitesh. Oh, no. Okay. So this is what we know is an hydraulic accumulator. So we use accumulator to reduce flow fluctuations. So this is an accumulator. So this accumulator, let's say you have a flow V dot in, you have outflow V dot out. This part is fluid. This is fluid. And here, this is air. So as you see, here fluid compressibility as well as air compressibility both come into picture. And if we have two springs, if you have two springs in series, these are basically compliances in series. So if you have two springs in series, excuse me, accumulator in this air compressibility is the predominant compressibility. And when you have two springs in mechanical series, let's say this is K hydraulic, this is K air, which is much, much less than K hydraulic, then this whole thing is equivalent to simply K air. Okay? So when you use an accumulator, it's basically the air compressibility that comes into play. So if this is air, then we can say this volume flow rate is V dot. So V dot air equal to V dot in minus V dot. this is the amount of fluid inlet, and original volume, total volume was V, total volume was V. We put, we take from that this part minus. So you have V dot. And here, V dot
Excuse me, sir.
is 0, this is 0. So you have minus V dot in minus V dot out. Okay, so that is the change in volume of the air, rate of change in volume of the air. So if we do that,
Excuse me, sir.
we can assume the whole temperature to be isothermal because fluid temperature will be the dominating temperature. So if we assume isothermal state,
Hello, sir. Hello. Hello, sir.
then we have E of air. Everything is air. E naught, E naught, or E. Yes, yes, I have seen. I have seen. I have seen already. Can be written as V dot in minus V dot out. If we integrate this fluid flow into the accumulator, we will get the fluid in the accumulator. And the rate of change of volume of air will be minus of rate of change of volume of fluid in the accumulator because total volume is constant. So we can write volume change rate of air is minus of V dot in minus V dot out. So we have a straightforward relation to find V dot air. Now, because this gas and liquid will remain in isothermal case, because the phenomena is very slow, we can assume it to be isothermal. Then Pv is equal to constant. We know some P naught, V naught. Initial pressure will be atmospheric pressure. Initial volume of the air will be full volume. Initially, everything was full of air only. So P naught, V naught. So we can find E is equal to P naught, V naught by V. Then we have a relation here which is highly nonlinear. What do we have? Effort is pressure, flow is V dot, of course V dot air. We are writing V dot air, that is V dot. Then we have a relation effort with some constant P naught V naught divided by integration of FDT. So this FDT has appeared in the denominator. So what kind of relation we have? We cannot write E is K integral FDT. This relation is for linear. Here we have a relation E is some function, let's say this is some kind of hydraulic function or accumulator function of integration of FDT. So this is a nonlinear relation, and this nonlinear relation will be shown by same C, but here we cannot write any parameter because it's not a linear thing. We cannot write a parameter. Rather, here we will write by the function, and within that, whatever arguments are there. So here effort is delta P, flow is V dot, but the parameter is not defined. We have some kind of a function. That's how one accumulator will be modeled. So accumulator is not a nonlinear spring. Sorry, accumulator is not a linear spring. It is nonlinear in nature. We have to model it like this. I will go for a linear spring, then another nonlinear one. Let's go for a open tank. Let's say we have a tank. This is a tank. There is water up to this level. Beside volume flow rate is V dot in. Volume flow out is V dot out. Let's say fluid is incompressible. Let us. So this total volume stored, this volume is integral of V dot in minus V dot out dt. So that is the total volume. Then pressure here at the bottom of this pipe, where whatever pressure we get at the outlet or inlet, so pressure we can write as mass of the fluid mgh, or we can write in terms of rho gh directly. No need to write all this. We can write rho is density, dh. Now this rho g are constants, and h is volume by area. So we have rho g by area integration of f dt, where f is rho to tank. What is it? V dot in minus V dot out. So you have here effort is pressure, total pressure at the bottom, flow is V dot, total V dot, and you represent this as C is to the effort pressure, so V dot, rho V by A. That's how a tank is modeled. Okay? So this tank, we have assumed that this top surface, this is open to atmosphere. Okay? So as this fluid moves up, this doesn't produce additional pressure. Whereas in the accumulator, we neglected the head due to this water. What we considered was the pressure due to the air, because that was dominating factor there. Here, the atmospheric pressure is negligible, it's everywhere same. What is dominating is the height of the head of the water. So we consider that as this kind of a linear model comes. Whereas accumulator gave a non-linear model. So that is for open tank. Let's go to last example of this C element. Let's say we have some kind of a mass M. Cb is its specific heat. Cb is specific heat. equal to mass. So MCB is heat capacity. Okay. Now to this we have some kind of input. Let's say Q dot, and its temperature is suppose T. So we will try to model it. We are not going to use variable Q dot. We will use the variables which give power. So what are they? For us, effort is temperature and flow is S dot, that is entropy flow rate. Flow or change rate. Unless we use this, the multiplication will not be power. Okay, so for this, we can write change in internal energy is TDS. We also know for this particular case, du is MCB dt, that is TDS. So we can write alternatively S equal to 1 by MCB. No, that's okay. MCB, not 1 by MCB dt by T. This we will integrate from some initial state to final state. So we will integrate both sides as usual. So I integrate ds from some S naught to S final equal to MCB constant. We take out T from some T naught to T final. Okay? So we now have S minus S naught. Let's say minus S naught T natural log, which is T final by T naught. Or we can write T final at, that is T at any given time T becomes take exponential part, okay, then multiply with T naught. Okay. T naught times e to the power S, say, st, S at current time minus S naught by M T B. So that is what we will get. Here, ST is basically flow. Sorry, total integral of flow. So we have a relation. Here you note that this E means EST. It means exponential. We have a relation where effort, temperature, flow is S dot T. So we have effort equal to from T naught exponential. I will write exponential. Some function phi of integral of S dot dt, which whole thing can be written as some nonlinear function, thermodynamic, let's say, integral of f t. So here you see this st, this is constant, this is constant, this is constant. So this st comes from integrating the flow, and it has entered into the equation in a very nonlinear way. So we find effort is related to flow, but in a nonlinear way. So this again is a nonlinear spring. So this is an energy storage in a pretty nonlinear way. The nonlinear energy storage here, effort is temperature. So it's a start. This C, which is given by some thermal accumulator as a function. This function means function of integral dt. Its argument is integral f dt. Okay? So that way we can find the temperature. So this is only thermodynamics for a single variable. Here you know E is kept constant. P, V, M, etc. dot are constant. In real thermodynamics, they will not be constant. Though it is not in your course, actual thermodynamics will be something like this. Full thermodynamics of a gas. E, there will be a multi-port C. Here effort will be pressure. Flow will be V dot. Here effort will be temperature. Flow will be S dot. Here effort will be specific enthalpy and flow will be M dot. That is 3-port C field. This is a matrix representation. This is not in your course. Okay? So there are other resistance elements and other things, but I have to answer a lot of pending questions. Let's see what is the problem. Let's try to fix this problem first. So how to fix this problem? So I am unable to hear. Let's check whether I am able to hear. Yeah. Hello. Ayush?
Yes, sir. You're audible, sir.
I can listen now. So there was some problem with that jack. So you ask one by one.
Hello, sir.
Yes. Who is speaking?
Pawan.
Pawan, yes.
Sir, why did you put the arrow from the system to this element, like for inertia element or C element or R element? Why did you put the arrow in the reverse order? Like the arrow is directed towards the C element, right?
Yes, yes, yes. Okay.
But for the source and effort, you have put it away from the
Yes.
element.
That is by convention. That is just by convention. Alright? Okay. That arrow doesn't say actually power goes in that way. Alright? Okay. Power can actually go opposite way. So that is just a convention. I will discuss later on how you will see that power moves from the system to the element or from element to the system. That also I will show you. Anybody else?
Hello.
Yes?
Yes, sir. Like here you have shown that this C is a 3-port element, but in last class you told that these I, R, C, these all are one port
One
elements
port
only.
element. Yes, yes, yes. I told. Okay. For your course, they are one port elements. Okay. For your course, they are one port elements. When you write those in matrix form, a matrix one port actually becomes something different. I can write the same thing as a matrix. Okay, all these three I can combine to a matrix. I can show it here itself in the screen. I am showing. So I have P here. My effort is E P H this vector transpose. Okay. Otherwise, I cannot take dot product, and my flow is corresponding terms. E dot. Oh, something will happen. Okay. E dot. Then you have S dot. Then you have N dot without transpose. Okay. So then E dot F you will get total power. Okay. You see, this is a vector. This when you take product with this is a one row vector, one column vector. We will take. Okay. So here this is row. Sorry, this one. This one is not transpose. We will take this one transpose. Okay. So when we take dot product, we will get total power. All right. So this we can write it in a form of a vector. So this is one port. But if I try to write it in form of a scalar, then it becomes three port. Okay, so this three port I have written in terms of a scalar. Actually, in practice, those will be written in terms of a vector and it will become one port. Three efforts are
Okay,
there,
sir.
three flows are there.
Okay, sir.
Okay, any other questions? Be very clear, ask everything. Yes? Uh, ask. What
Hello.
is it?
Uh,
Yes, yes.
so, uh, so I was just saying that if you could enable the chat, like we cannot type messages on the chat.
Is that?
Yes, sir.
Cannot write messages on the chat. I don't know where it stopped. Its chat I have one. Okay. Ayush Kumar's message I am seeing. Okay. 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 So Ayush, find out the option. Okay. Eh? Somewhere that option is missing. Right. I have to check where is that option. Okay. No, that's not a problem. We have full rights to manage the group. Okay. I don't, I will check that. Right now, you would answer all kinds of questions related to the material because I think there were a lot of questions. Yes.
Yes, sir. Yes, sir. Yeah, so
Uh,
like when I start speaking, it gets muted. Then sometimes, yesterday it was continuous. I was getting removed from the meeting, etc.
uh,
Those problems were there.
can somebody outside the administrator remove you from the meeting?
So,
I have been
like,
muted several times.
like whenever I start speaking, I get muted multiple times, again and again.
So I think
No.
everyone has the option to mute and remove people from the meeting.
Then there is no way to stop that.
No, there should be an option to do.
No,
There is an option, sir, because in the other classes we don't have this option.
but I have put that.
Just now I had been muted, and it is showing that
Sir,
someone
we
muted
have
me.
required to put the restriction.
Okay, I will check. I will check and put the restriction. Okay.
Yes.
But anything related to the lecture all these things, if you have any problems, you just ask. Ayush has anyway recorded everything. It seems like he has recorded, maybe some breaks was there. So you ask whatever is related to this. I am stopping, and we have a class tomorrow evening, 8 to 9:30. And as you know, you must be having other classes also, other day, night, 8 to 9:30.